everyone, I'm a Huawei engineer. Today, I will introduce the MSTP feature of Huawei enterprise switches. On complex networks, to implement redundancy, network designers tend to deploy multiple physical links between two devices, one of which is the master and the others are the backup. Loops may occur on the network. Let's look at the figure. If host A broadcasts a request message, the message is received by port 1 and port 3 and forwarded by port 2 and port 4. Then port 2 and port 4 receive the message sent by the other device, and port 1 and port 3 forward the message. The procedure repeats and a loop occurs. Then the CPU usage and port rate increase, and MAC address flapping alarm is generated. Then network resources may be exhausted and the network breaks down. As a result, MAC addresses are damaged and services are interrupted. You can use STP to prevent loops on the network. Switches run STP, exchange STP, bridge protocol data units to discover loops on the network, and block some ports to prune the network into a loop-free tree network. MSTP prevents infinite looping of packets to ensure packet processing capabilities of switches. Next, I will introduce STP implementation. First, the root bridge is selected according to the bridge IDs. A bridge ID consists of the bridge priority and MAC address. The bridge with the smallest ID is the root bridge on the network. All the ports rows of the root bridge are designated ports. Then each of the downstream bridges connected to the root bridge selects the most robust branch as the path to the root bridge, and the corresponding ports become the root ports. Repeat the preceding process at the network edge. After the designated ports and the root ports are specified, a tree is generated. After a certain period, the designated ports and the root ports of the spanning tree enter the forwarding state, and other ports enter the blocking state. STP BPDUs are sent from the designated ports of each bridge to maintain the link status. If the network topology changes, the spanning tree is recalculated and the port status changes. Huawei enterprise switches support STP, RSTP, and MSTP. This table lists the disadvantages of STP and RSTP. STP cannot provide fast convergence. STP and RSTP cannot implement VLAN-based load balancing because all the VLANs on a VLAN use the same spanning tree. After the link is blocked, it cannot carry any traffic. This wastes bandwidth and may cause a failure to forward VLAN packets. To offset the disadvantages of STP and RSTP, the IEEE released 802.18 in 2002 to define MSTP. MSTP is compatible with STP and RSTP, implements fast convergence and VLAN-based node balancing. Next, I will introduce the basic concepts to you. All the devices in the figure run the STP protocol. Next, I will explain basic concepts of MSTP. First, MST region. An MST region consists of multiple switching devices and network segments between them. All the devices in the MST region are enabled with MSTP. They have the same MST region name, VLAN MSTI mappings, and MSTP revision labels. All the devices are physically connected. The 4 devices in the region A0 form an MST region. Second, VLAN mapping table. The VLAN mapping table describes the mapping between VLANs and MSTIs. Let's look at the figure. VLAN 1 maps to MSTI1, VLAN 2 maps to MSTI2, and other VLANs map to the CIST in the MST region A0. Third, CST. A common spelling tree, CST, is a spelling tree that connects all the MST regions on the switching network. If each MST region is a node, the CST is a spelling tree calculated by using STP or RSGP based on all the nodes. The CST is constructed by connecting all the regions through yellow lines. Fourth, CIST. Common and internal spelling tree, CIST, is calculated by STP or RSGP. It is a single spelling tree, also known as SST, that connects all the switches on the switching network. In the figure, the ISTs of all the MST regions and the CST compose a complete spelling tree called CIST. Fifth, CIST root. The CIST root is the root bridge of the CIST. It is a device in the region A0. Sixth, regional root. Regional roots are classified into IST and MSTI regional roots. The figure shows an IST regional root. In B0, C0, and D0, the IST regional root is closest to the CIST root. An MST region may contain multiple spelling trees, each of which is an MSTI. The MSTI regional root is a tree root of each MSTI. Different MSTIs in the MST region have different regional roots. MSTP also involves the following concepts. First, region edge port. Second, bridge ID. Third, external path cost. Fourth, internal path cost. Fifth, designated bridge ID. Sixth, designated port ID. MSTP ports have 7 rules, including root port, designated port, alternate port, backup port, edge port, master port, and regional edge port. Next, I will explain port rules. First, root port. Second, designated port. Third, alternate port. Fourth, backup port. Fifth, master port. Sixth, regional edge port. Seventh, edge port. MSTP divides a layer 2 network into multiple MST regions. CSTs are generated by calculation between regions. In the region, multiple spelling trees are generated, and each spelling tree is an MSTI. MSTI0 is called IST. Similar to STP, MSTP calculates a spelling tree using configuration messages, that is, BPDUs. The BPDUs carry the device MSTP configuration. First, CIST calculation. After configuration messages are compared, the device with the highest priority is elected as the CIST root. MSTP calculates and generates an IST in each MST region. MSTP considers each MST region as a device and generates the CST among MST regions. the CST and ISTs form the CIST on the entire switching network. Second, MSTI calculation. In the MST region, MSTP generates different MSTIs based on VLANs. Each span tree is calculated in the same way as the STP calculation. MSTP also supports the following functions. First, implements fast convergence by the proposal agreement mechanism. Second, provides protections. MSTP enables the switch to forward packets from different VLANs on the same network based on different spanning trees. This implements load balancing and backup of data from different VLANs. Switch A and Switch B are aggregation devices, and Switch C and Switch D are access devices. To load balance traffic on links, configure the switch as follows. All the switches must be in the same MST region. Packets from VLAN 10 are forwarded along MSTI1. The root bridge of MSTI1 is Switch A. Packets from VLAN 20 are forwarded along MSTI2. The root bridge of MSTI2 is Switch B. Packets from VLAN 30 are forwarded along MSTI3. The root bridge of MSTI3 is Switch A. Packets from VLAN 40 are forwarded along MSTI4. The root bridge of MSTI4 is Switch B. After MSTP calculation is complete, packets from different VLANs are forwarded along different paths, which reduces the load of each link. In addition, each VLAN has a standby link. When the active link fails, the standby link works immediately. This prevents packet loss due to the link fault. The following figure is a typical MSTP networking diagram. Let me show you the key configurations and precautions in MSTP deployment. First, configure a VLAN and add ports to the VLAN. Create VLAN 10, VLAN 20, and VLAN 30 on Switch A and Switch B respectively. Then create VLAN 10, VLAN 20, and VLAN 40 on Switch C and create VLAN 20, VLAN 30, and VLAN 40 on Switch D. Set the link type of ports on the switches to trunk and allow packets from the corresponding VLANs to pass through. Second, configure Switch A. Set the name of an MST region to example. Map VLAN 10 to MSTI1, VLAN 30 to MSTI3, and VLAN 40 to MSTI4. Configure the local switch as the root bridge of MSTI1. Enable STP globally. Please note that you must run the active region configuration command to activate configurations in the MST region so that the domain name, VLAN mapping table, and the MSTP revision label take effect. Otherwise, MSTP configurations do not take effect. Third, configure Switch B. Set the name of an MST region to example. Map VLAN 10 to MSTI1, VLAN 30 to MSTI2, and VLAN 30 to MSTI3. Configure the local switch as the root bridge of MSTI3. Enable STP globally. Fourth, configure Switch C. Set the name of an MST region to example. Map VLAN 10 to MSTI1, VLAN 20 to MSTI2, and VLAN 40 to MSTI4. Configure the local switch as the root bridge of MSTI4. Enable STP globally. Configure GA100 as 8 port and enable BP BPDU protection on the port. Fifth, configure switch D. Set the name of an MST region to example. Map VLAN 20 to MSTI2, VLAN 30 to MSTI3, and VLAN 40 to MSTI4. Enable STP globally. Configure GE100 as an 8 port and enable BPDU protection on the port. Now, let's move on to the common faults. Fault 1. Services are interrupted when the MSTP topology changes. The possible causes are as follows. First, MSTP configuration is incorrect. Second, the physical link flaps. As a result, the switch sends a large number of TC BPDUs. The troubleshooting procedure is as follows. First, check whether MSTP is working properly on the switch. Run the display STP brief command to check the connectivity of ports on the MSTIs. Second, check whether MSTP is correctly configured. Run the display STP region configuration command to check the mapping between VLANs and MSTIs. If the mapping is incorrect, run the instance command to map a specified VLAN to a specified MSTI, and then run the active region configuration command to activate the preceding configuration. Run the display current configuration command to obtain the configuration file and check the MSTP configuration. Check whether the MSTP enabled port is configured to send BPDUs. Check whether the port connected to the user terminal is enabled with MSTP or configured as an 8 port. If a BPDU tunnel is configured on the MSTP enabled switch, check whether the BPDU tunnel is correctly configured. Check whether the port is added to the correct VLAN. Third, check whether the ports alternate between up and down. View the log if late for if state to check whether there is an MSTP enabled port whose status changes between up and down. If the port exists, shut down the port. Fault 2. A fault occurs when the switch communicates with a non-Huawei device. The possible cause is as follows. First, the BPDU keys of the switch and non-Huawei device are different. The troubleshooting procedure is as follows. First, run the STP config digest sloop command on the port to enable digest slooping. If you want to know more about the MSTP feature of Huawei Enterprise switches, please go visit our website enterprise.huawei.com. Thank you for watching.